This is a video for solving trig equations for pre-calculus. And we're just going to go over some general ideas of what it is to solve these trig equations. And first up is we need to look at the possible, what kind of answers we're looking for. We could have two different ways that you could be asking, that answers could be asked for. And one is when it's just involving in one revolution of a circle, meaning your angles would be between 0 and 2 pi, not including 2 pi. Or it could be asking you for all possible answers. Let's look at a very simple one to start off with. When we're saying that sine of x equals root 3 over 2, we're trying to figure out all the different places that this would be true. And we can see, if we think about what we know in the unit circle, we know that this will be true at the angles pi over 3 and 2 pi over 3. But not only that, it's true for infinitely many different angles, and there's a pattern to those angles. And if we look at the unit circle itself, the pattern is we started off with pi over 3 and 2 pi over 3, then we went all the way around the circle, 2 pi, to get back, so it's coterminal with pi over 3, and that's where 7 pi over 3 is. And then we got over here another coterminal at 8 pi over 3. We could keep going around and around and around. Every time we go around, we go another 2 pi, but we're constantly landing on these two spots, coterminal. We could also go clockwise negative, and we could have negative 5 pi over 3, or, and so these, actually that'd be negative 4 pi over 3, and then we have negative 5 pi over 3. So going in the clockwise direction, we could also have angles. If we look at this graphically, we can see here this red line represents where the curve would go all the way up to root 3 over 2, and it intersects this sine wave infinitely many times. The sine wave kept going on and on and on. And so therefore, when we look at the pattern, the answers are pi over 3 plus multiples of 2 pi, as well as 2 pi over 3 and multiples of 2 pi. But we have a way to write multiples of 2 pi, and that would be 2n pi. The other way I say it is any 2 pi. And so this is the way we would answer if the question for this problem, sine x equals root 3 over 2, was when we wanted all possible solutions. We would say it's pi over 3 and any multiple thereof, any multiple of 2 pi, or 2 pi over 3 and any multiple of 2 pi. But if we were being asked and said, okay, have your x's belong to the set of 0 to 2 pi, not including 2 pi, then you would just have these two answers alone, pi over 3 and 2 pi over 3. You would not answer with all of these other numbers. So, general idea of how to solve. We got a bigger equation. This one was rather simple. It just was already set up. It was already just had to think of what the x's would be. So general idea is when you have a bigger equation with a couple different terms, you're going to add or subtract to get the equation equal to 0. Then you'll be able to factor something out and use the zero product rule to solve. And this is very general. The factoring is similar to that of polynomials, and sometimes, because it won't look like a polynomial to begin with, you might have more than one trig function. Sometimes you're going to use identities so that you'll only have one trig function in the equation. That's not always the case. It's just these are general methods and general ideas to look for. This last one, though, when you have multiple angles in an equation, meaning you've got something like sine of 3x equals root 3 over 2, instead of sine of x equals root 3 over 2, you're going to solve for that 3x, or that 3 theta, and you're going to always start solving as if the x could be anything, a set of real numbers. And then you would divide by that coefficient in front of the angle to finish solving for whatever set was being asked for. Let's start with this problem here. And we do note that the answers are only in one revolution of a circle, 0 to 2 pi, not including 2 pi. Step number 1 would be to set this equal to 0 using addition or subtraction. So we're going to subtract 2 tangent of x. Again, you don't want to use division, because if you were to divide by tangent of x could be 0, and you might be dividing by 0, which would be a real bad thing to do. We notice that both of these terms have tangent of x, so we factor out the tangent of x. Even though we've got two different functions, the sine function and the tangent function, because we were able to factor one of the functions all the way out, everything's fine. We use the zero product rule, meaning we divide this up into two different groups. One factor equals 0 or the other factor equals 0. Solve each one of these separately. So I'm thinking about where is tangent of x equal to 0, and that'd be at 0 and pi, 2 pi, 3 pi, 4 pi, 5 pi. Infinitely many pi is when this where tangent would equal 0. But remember that we're asked for answers only in one revolution of a circle, so 2 pi won't work. In this case, for this one here, the only answers are 0 and pi. Now we take our attention over to this other factor. We're going to add 2 to both sides, taking the square root. And then we pause for a moment and think about the square root of 2. The square root of 2 is greater than 1. And sine is never more than 1. Sine of x, just plain old sine of x, is never more than 1. So therefore, that can't happen. And this is an extraneous solution. And that's going to happen sometimes. Is you're going to have some number that will come out algebraically, but it doesn't make any sense. You cannot have an angle that will ever have a ratio greater than 1 for sine. So in this problem, the only answers are x is equal to 0 and pi. Problem number 2. If you look at this carefully, this actually resembles a quadratic. We've got a 2 times something squared plus 1 times something minus 1 equals 0. Well, that factors. So we have these two factors. We now use the zero product rule, breaking up our two factors, having them each equal to 0. We're going to take this first side. We're going to solve this for sine of x. So we're going to add 1 and then divide by 2. And we have to remember what angles is sine of x equal to 1/2, noting that we only need to talk about answers that are in one revolution of a circle. And so we have pi over 6 and 5 pi over 6 and maybe 13 pi over 6. Whoops! 13 pi over 6 is more than one revolution of a circle. So we would stop after 5 pi over 6. Now we're going to turn our attention over here. And we subtract the 1. That's perfectly fine. Where is sine of x equal to -1? And that is all these different places. And once again, we can't go more than one revolution of a circle. And one revolution of a circle is no more than 4 pi over 2 is 2 pi. So these answers don't work out. But we do have these two, and we also have this one. And so therefore we have the 3 different angles for which this equation would be true. Any one of these 3 plugged in would make this equation true. Equation number 3. Now here we have cosine squared and just sine. Now it kind of looks like a polynomial, except that we've got 2 different functions. We can't have that. So we look at the 2 different functions, cosine squared and just sine. We can't change the sine into cosines, but we can change cosine squared into something with sines, and that is 1 minus sine squared. We distribute the 2. Now we have a 2 here and a -3, so we need to collect like terms. I don't like having a leading term negative, so we're going to multiply the whole equation by -1. And now I have what resembles a quadratic. 2 times something squared minus 3 times that something plus 1 equals 0. That factors the zero product rule. And I'm going to start over here and solve this group. And I get pi over 6 and 5 pi over 6. Now we're going to turn our attention over here and add the 1. We just did that a few moments ago. And so we have those 3 angles. And so my answer for this problem, and it's all the way up here, this one with cosines and sines, these 3 angles, any one of those 3 plugged into this equation would make that equation true. And here we have a different one here. Now we've got one that has a multiple angle in it, a 3x. Well, remember this is just an angle, so if you just wrote theta here, we don't care that it says 3x right now. It's just that there's an angle, I'm going to cover it up, there's an angle where 2 times cosine of that angle, it equals 1. Step number 1 would be divide by 2, so you'd have cosine of an angle equals 1/2. And so we have this. Now, thinking about what angles does cosine equal 1/2, and that would be pi over 3 plus any 2 pi and 2 pi over 3 plus any 2 pi. And at either one of those, the cosine would be 1/2. It was a mistake here. It was 5 pi over 3 plus any 2 pi. So now, once we've identified that we have these two different places, pi over 3 and 5 pi over 3, plus any 2 pi, we have to turn our attention to the fact that these each say 3x equals, and we want to solve for x. So starting with this one up here, we're going to divide everything by 3, or in this case, multiply by 1/3. And when we do that, we end up with x equals, and then you have to distribute that 1/3, so we have pi over 9 plus 2/3 times n pi. So this is any 2/3 pi is what's going to happen. So start adding those up, and so you start with your pi over 9, and you're adding 2 pi over 3, otherwise known as 6 pi over 9. So you keep adding 6 pi over 9 plus 6 pi over 9 plus 6 pi over 9, and we have this list. Remember that when we started this, it says start by solving over all of r. That's why we had the plus 2n pi. But the reality is we only want to go one revolution of a circle, and perhaps you can see that 19 pi over 9 is too far. So that is not part of our solution set. Only those 3 angles are. And that's rather interesting. This said 3x, and we ended up with 3 different angles for this part right here. Now we're going to do the same thing to this other angle, 5 pi over 3 plus any 2 pi. Multiply both sides by 1/3 so that we have x equals. And so we're starting with 5 pi over 9 and adding multiples of 2/3 pi. But remember, 2/3 is the same thing as 6/9. So we start adding 5 pi over 9, and then we're going to add 6 pi over 9, and another 6 pi over 9, and another 6 pi over 9, and another 6 pi over 9. But we look at this list, and some of these are too much. They're more than one revolution of a circle, so we get rid of those, and we have those 3. Now, that might, you might want to do a little bit more research, but is this a coincidence that it had a triple angle, 3x, and for each one of these spots that we first solved for, there really were 3 answers? The full answer to this problem are all 6 of those angles. And so any one of these 6 angles, when plugged into this equation up here, it would be true. And all 6 of those angles are in this solution set of between 0 and 2 pi. Next problem. Well, in this problem we have terms on both sides of the equal sign, so we're going to subtract the 5 sine x, and we're going to add the 3 to make this equal 0. And now we have a much simpler problem, so we're going to add 1 to both sides and then divide by -2. And when we do that, when we divide by that -2, we get -1/2. And where sine of x is -1/2, that would be at 7 pi over 6 and 11 pi over 6. Sorry, I had a mistake there at first. Fix that though. At 7 pi over 6 and 11 pi over 6. But remember, since this time, you look at the solution, they needed to be all real numbers, so therefore you have to leave this any multiple of 2 pi after each one of them. And our last one, again, it is a set of all real numbers. So we've got this problem. We're going to subtract, so we're going to add 3 and then divide by 4. Then we're going to take the square root, and we get both positive and negative square root of 3 over 2. And in the unit circle, you start looking at all of these possibilities in one unit circle and realize there's a pattern involved. That to go from pi over 3 to 4 pi over 3, we would have just added pi. And also, to go from 2 pi over 3 to 5 pi over 3, we would have just added pi. So in this case, we're not going to write each one of these 4 and then say plus multiples of 2 pi. We could just start with pi over 3 and say multiples of pi, because every time you add pi, you're going to land on either pi over 3 or 4 pi over 3. And if you started with 2 pi over 3 and kept adding pi, you're either going to start with land on 2 pi over 3, or you're going to land on 5 pi over 3. So that's the final answer for that problem.